again, sorry, people have heard this 3 or 4 times already. After this talk, we're going to have the open problem session, and I haven't heard from many people yet. And so if you're interested in giving an open problem, please let me know after the talk. So we have the pleasure of having Shayan Ove-Garan speak to us today about structural properties of low threshold ring graphs. Thanks.
Hello, thanks a lot for inviting me. So this is a talk probably very different from what you heard today. It's going to be a sort of a survey talk, so I try to not go into too much math. There's going to be a short proof at the end of the talk, but it's more kind of overview of this area. So the plan is to talk about this family of graphs called low threshold rank graphs that are essentially a generalization of expander graphs. Okay, so I'll talk about them shortly, define them shortly. So let me start by telling you like this field that I'm coming from. So it's called spectral graph theory. If you're not familiar with it, what we do in general is that we study graphs and prove structural properties of graphs by looking at eigenvalues and eigenvectors of adjacency matrix or the Laplacian matrix of the graph. So let me first set up some notation and then tell you some of the results in this field. So okay, throughout the talk, I'm going to assume that G is an unweighted irregular graph. This is just for the simplicity of notation, but I mean everything I'm going to talk about will extend to weighted non-regular graphs. I'm going to assume that it has n vertices. So there's going to be 2 set of matrices you can associate with this graph, normalize the adjacency matrix and normalize the Laplacian matrix. So normalized adjacency is just A would be the adjacency matrix I'm going to use. So A over D would be normalized adjacency matrix, and I minus A over D would be normalized Laplacian matrix. So I'm going to use lambda 1 up to lambda n to denote the eigenvalues of this normalized adjacency matrix. When you divide by D, you can easily show that the eigenvalues are always within this range, like 1 to minus 1. And if you look at the normalized Laplacian, the eigenvalues would be 1 minus lambda 1 up to 1 minus lambda n. Okay? So the smallest one is 0, and the largest one is at most 2. Again, so throughout the talk, lambda 1 would be largest eigenvalue of the adjacency matrix, and so on and so forth. Lambda 2 would be second largest. So I'm going to assume that many of you are familiar with expander graphs. If not, it will be clear as we go along. We say G is an expander graph, like epsilon expander graph, if the second eigenvalue of the normalized adjacency matrix is at most 1 minus epsilon. Okay, so here is an example of a graph. If you look at the cycle of length 4, it has 4 eigenvalues, and I guess, oh, sorry, this should have been a 1. So the first eigenvalue is a 1, then the other 2 are 0, and the last one is a minus a 1. Okay, good. So any questions in this? Okay, so here are some classical results in a spectral graph theory. There are many more that I'm not covering here, but okay, so as you see in these classical results, you typically look at the second largest eigenvalue or the last sort of smallest eigenvalue. And then by looking at those eigenvalues, you say something about the graph. So let me briefly say, so if lambda 2 is very close to 1, then you can say that G is almost disconnected, meaning that there is a cut of very small size with respect to its size. If lambda 2, so I use this notation to say it's bounded away from 1. So if lambda 2 is bounded away from 1, we say G is an expander. So this combinatorially means that every set of the graph has a lot of neighbors and a lot of edges going out of that set. Then there is this regime where both of the second and the last eigenvalue are very close to 0. So this is the regime that so-called expander mixing lemma kicks in, and you say that G is very similar to a random graph, to a random irregular graph. And then the last thing is when the last eigenvalue is very close to minus a 1, then we can show that G is close to a bipartite graph. There are many other things you can also show. For example, you can look at the second eigenvalue and talk about the diameter of the graph, graph coloring, and so on and so forth, that some of the audience here have been worked on. Okay. So the main sort of plan of this talk is to study generalization of this statements, structural statements, to higher eigenvalues. So what I'm going to do is that I'm going to define a sort of a family of graphs that we call low threshold rank graphs. These are like you can think of them as generalization of expanded graphs. The nice thing is that once you know these low threshold rank graphs, you can study all of these structural properties in them, and then see how these properties would naturally extend to these low threshold rank graphs. This would allow us to sort of generalize many of these properties to higher eigenvalues. Okay, so the thing is, when you want to generalize this from 2 to kth eigenvalue, you may not know what would be the analog. Like one way is to look at these low threshold rank graphs and then based on them guess something and prove a generalization. So let me first define these low threshold rank graphs. So we say, let's say you have a graph G, again it's deregular. The epsilon threshold rank of G is the number of eigenvalues of, again, normalized adjacency matrix, which are at least like epsilon in absolute value. Okay? So it's good that for the sake of this talk, think about low threshold rank graphs as graphs where this rank epsilon is at most a constant for some small epsilon. Okay? So sometimes it's good I'm going to have epsilon to be like a constant, like 1/2, and sometimes we need it to be smaller, like closer to 0. But typically think of it as a small constant. Okay? So this is what I mean by low threshold rank graphs. I'm going to use this definition throughout the talk. Okay? So let me first give you some examples of these low threshold rank graphs. The first one is a so-called Ramanujan expanded graphs. So in these graphs, if you look at the eigenvalues of the adjacency matrix, the first normalized adjacency matrix, the first one is 1, but everything else is between like minus like 1 over 2 root t and plus 1 over 2 root t. Okay? So you can show that basically the number of eigenvalues bigger than this number is 1, is exactly 1. Okay? So these are like probably the best low threshold rank, the best kind of low threshold rank graphs you can hope for. In general, I allow this to be a constant, more than 1. Okay? Here is another example. So let's look at dense graphs. So think of a regular graph where every vertex has a large degree, like constant times n degree. Okay? So I claim that these dense graphs are also low threshold rank. So let's see the proof. It's like one-line proof. So let's look at let's look at the Frobenius norm of the normalized adjacency matrix. So this is just a summation of the square of all of the entries of A over D. Okay, you can simply take this 1 over D out. It's going to be 1 over D squared, the Frobenius norm of A. And the Frobenius norm of A is just, because it's deregular, this is exactly n times D. So you get n over D. Now, on the other hand, you can write the Frobenius norm as a summation of the square of the eigenvalues. That's another identity you can, like the eigenvalues of A over D. Okay, let's not go to the proof of it. Okay, this is an identity you can easily prove. And then once you have this, okay, there are only this many eigenvalues bigger than epsilon. So this quantity is at least epsilon squared times rank epsilon. Okay? There are this many eigenvalues greater than epsilon. So okay, so you exactly get this. Now you move things around, you get that rank epsilon, like for any epsilon, rank epsilon is at most this much. Now, if D is like constant times n, I'm going to get that this is a low threshold rank graph.
Epsilon should be in the denominator.
Yeah. Epsilon should be in the denominator. Yes, very good. Thanks. Yes. Okay. So because of this, like some of the theorems, like theorems that I'm going to talk about, actually generalize many of the results that you know about dense graphs as well. Okay. And again, results are not. You don't necessarily need the graph to be regular. Like they work even if the graph is not regular. But this is just for the simplicity of notation. Okay. So let's start with a structural theorem for low threshold rank graphs. So So the theorem I'm going to talk about again is for any graph, but I'm going to tell you an application to low threshold rank graphs. So here is a theorem I proved with Luca and sort of generalized as a result of Tanaka. So here is the statement. If you have any graph G and any number K, there is a partitioning of G into, say, K sets such that each of them is this good an expander. So what is this? This is like 1 minus lambda k plus 1 squared over k to the 4. Okay? So forget about this k. So think of the, suppose you have a low threshold rank graph, and let's see what this says. So if you have a low threshold rank graph, it means that for some, say it means a rank of, if you look at rank of 1/2, the eigenvalues which are more than 1/2 in absolute value, they're at most a constant. So you let this k to be that constant, and that lambda k is like 1/2 or less. So this says that for a constant k, this whole number is a constant. That means that you can partition your graph, your low threshold rank graph, into many expanders such that each of them have second eigenvalue this much. Okay? So because of this, you can think of low threshold rank graph as a union of expander graphs. Okay? And basically, the number of expander graphs that you get is essentially comes from this rank of epsilon, or rank of a constant.
Does it tell you anything what happens between the sets?
We can also say things about that. So if there are gaps, for example, between eigenvalues, you can say that these cuts are very sparse. So there are very few edges in between. Okay. So at least structurally, you can think, yes?
The gap needs to depend on k?
The gap, okay, so it depends if you want to say it in terms of eigenvalues or in terms of so-called conductance of sets. If you want to say in terms of eigenvalues, yes, you need a big gap, both depending on k. So you need lambda k plus 2 to be root lambda k plus 1 times the polynomial of k, something like that, if you want to say the gap in terms of the eigenvalues.
Is the gap that you need just between k and k plus 1?
Yeah.
Or,
yeah, just one gap is enough to get, yeah. And it doesn't depend on n. It just depends on k and the eigenvalue. Yeah.
Yeah. So, in terms of a converse to this, so if lambda k plus 1 is close to 1, then
Yes.
what can you say?
Then you can say that you can partition your graph into k sets of small conductance. I'm going to say conductance in a few slides, but yeah, you can partition your graph into k sets of small conductance. Okay. I won't focus on the converse to this, but there's a whole theory that we prove for the converse of this, that the regime where like lambda k is small. Like here, I'm mainly focusing on the case where lambda k is bounded away from 1. Okay, good. So now that you have this, you can say, okay, now let's look at these graphs, right? So what property, if you have a graph which is union of expanders, what other structural properties does it have? The probably easiest one would be the diameter, okay? The diameter of an expander is log n. So if you have k expanders, the diameter is at most k log n, okay? So this is the sort of another theorem we proved that, again, the theorem is independent of the graph, independent of the graph to be low threshold and holds for any graph. That for any graph G and any k, the diameter of G is at most k log n over 1 minus lambda k. Okay, so if lambda k is bounded away from 1, the diameter is at most k log n. Okay? And again, there are theorems for lambda 2 versions of this that some people here have been working on. Here again, the nice, the point is the generalization to k. Okay. So yeah, so if rank of 1/2 is a constant, you get this times log n diameter. Okay, good. So now we understand diameter. Now let's look at another property, the eigenvectors of low threshold rank graphs. Can we talk about the eigenvectors of this graph? Now, morally, what you expect is that you have a lot of expanders, and say there are a few edges in between. So what I expect, I expect that the first few eigenvectors to be constant on expanders. basically focus on the cuts separating the expanders. Okay, and this is sort of this is the intuition behind this theorem that we proved. It is with Koch, Lee, Lau, and Trevisan. That again, it's for any graph. You don't need low threshold rank graphs, but you can. I'll show you the theorem tailored to low threshold rank graphs. So if you have any graph G and you look at the ith eigenvector of like the eigenvector Vi of lambda I, then it says that you can very well approximate Vi by a 2k step function. Okay, so by 2k step function, I mean something like this. Say this is Vi. Like I've sorted the vertices of the graph based on their value of Vi, and what I mean approximating by a 2k step function, I mean a function that only takes 2k different values, and the difference between this function, this 2k step function, and my eigenvector is very small. Okay, so how small can we prove? It depends on the lambda I and lambda k. If lambda I is close to 1 and lambda k is bounded away from 1, then this is a very good approximation.
It's L2 norm.
This is L2 norm, yeah.
So you lose a factor of 2 because there are k expanders and you expect them to be a k step function?
So how many expanders are there if lambda k is
I'm not assuming that this is for any graph.
but like in the low rank,
Yeah,
so you lose a factor of 2.
you lose a factor 2, but that's like a technicality that you lose. I guess if you don't want to lose a factor of 2, you can pay a factor of k here, and then don't lose a factor of 2 in that. But yeah. So again, if G is a low threshold rank graph, in the sense that you have few big eigenvalues close to 1, and the rest of them are close to 0, then this lambda I is close to 1, so this is close to 0. The denominator is a constant, so you can approximate. So basically, what this says is that the first few eigenvectors are sort of constant or approximately constant on each expander. Okay, so in other words, just by looking at these eigenvectors, you should be able to figure out the underlying expanders. So now you can strengthen this theorem I just described to prove a so-called generalization of Chigir's inequality. I haven't defined what Chigir's inequality is, but let me say and then tell you what this generalization is. So I need this definition. Hopefully many of you are familiar with it. So this is so-called the conductance of a graph. So I have to give you a 1-minute introduction. So if you have a graph G, you can define the conductance of a set to be this ratio. It's a ratio of the edges leaving the set to the summation of the degree of vertices in the set. Okay? So if you have a set of a small conductance, it means that there are very few edges leaving this set as opposed to the degree of the vertices, or the number of edges incident to all of these vertices. Like again, a good intuition to have in mind is that if this is a social network, these represent like a friendship between individuals. If you have a set of a small conductance, it means that you have a group of individuals who are mostly friends with each other as opposed to outside. Now, the conductance of the graph is basically the worst conductance is the worst conductance among all sets in the graph. The set with the smallest conductance, you need the size of the set to be small. This is a technicality, don't get into it. So it's essentially the worst conductance in the graph. Now, what Chigir's inequality says is that, so in the classical Chigir's inequality, instead of this right-hand side, you have 2 root 1 minus lambda 2. Okay? So basically what classical Chigir's inequality says is that just by looking at the second eigenvalue of this normalized adjacency matrix, you can characterize the conductance of the graph. Okay? Now what we sort of prove and improve this, we said that if you tell me something about the kth eigenvalue, and especially if this kth eigenvalue is bounded away from 1, I can dramatically improve the Chigir's inequality. Okay? So in particular, if this lambda k is a constant bounded away from 1, this is going to be a constant in the denominator. So the left-hand side and the right-hand side are the same up to a factor of k. So as you see in the original Shigeru's inequality, there is this square root gap between the left and right hand side, which can be huge. Like it can depend on n in general, but this is saying that if for example, a small k, lambda k is bounded away from 1, the left and right hand side are very close. And again, so let's think of the intuition. So suppose you have a graph where lambda k is bounded away from 1. Okay, what does this say? Like by the result I just said in the last slide, you expect the second eigenvector to be constant on expanders, okay, or approximately constant on expanders. On the other hand, if you look at the conductance of the graph, this phi of g, you don't expect it to sort of cut through expanders. Because if you cut through expanders, you're going to cut a lot of edges, and you're not going to get a set of a small conductance. Okay? So in general, you expect the optimum phi of g to be something like this. Cut between expanders. And this is this is saying that, okay, if this is the case, why should you expect the second eigenvector to, or the second eigenvalue to very well characterize phi of g? Because the second eigenvector are constant expanders, so the corresponding eigenvalue should only depend on what is going on in between, and you shouldn't lose the square root gap that you would in the original Shigeru's inequality. Okay. Actually, you can even say more. Not only you get this, if you try more, if you're willing to expand like a 2 to the k time algorithm, you can essentially recover these expanders and look at all possible sort of way you can partition this graph into 2 sets and approximate the phi of g to a constant factor, to a very small constant. So okay, so this last part of the, I have a few minutes. Okay, good. So in general, this study of low threshold rank graphs started from basically these 2 papers, Kolla and Tulsiani and Arora Barak-Stuer. The goal was to understand and design algorithms for unique games problems. This area led to these nice algorithms called subspace enumeration. Basically, the idea is that if you have a low threshold rank graph, if you look at the eigenvectors corresponding to the first few eigenvalues, you can brute force over all linear combination of them and solve most of the interesting optimization problems on these low threshold rank graphs. Afterwards, there are very nice extensions. You can use semi-definite programming and approximate many more problems like constant satisfaction problems, etc. Let me not go into it on this graph. So essentially, like the high level is that on expanders many problems are easy. On low threshold rank graph still they are easy, but you have to pay a factor exponential in the threshold rank. Okay, so if the threshold rank is a constant, you only pay a constant more. But as it gets bigger and bigger, you're going to pay more and more to solve your optimization problem. Okay, now I want to finish this talk by giving you a last like a third approach to design algorithms for optimization problems on low threshold rank graphs. So this is based on a result I had with Luca. What we show is that we prove a sort of a weak regularity lemma for low threshold rank graphs. So basically, this gives another way to solve these optimization problems. In particular, I'm going to focus on max cut, but this gives you another way to design algorithms. So let me first remind you of weak regularity lemma. This is the statement of theorem proved by Friese and Cannon. It gives a simpler characterization of dense graphs using so-called cut matrices. I guess the reason these guys come up with this is that, first of all, it gives a very simple proof compared to the original regularity lemma, the proof here is much simpler. And secondly, it gives very fast algorithms to approximate max cut in dense graphs. Okay, so let me first say their theorem, and then I'll say how we generalize it to low threshold rank graphs. Okay, so here is a theorem that Friesen Cannon proved. They said that for any graph G and any given epsilon, you can find, essentially 1 over epsilon squared cut matrices. I'm going to say in a second what cut matrices are, such that the adjacency matrix can be very well approximated by a linear combination of these cut matrices. So what is a cut matrix? This is a cut matrix. It's essentially just a 0-1 matrix where the one part is a rectangle in this matrix. Okay, so a cut of SITI, what happened here, is this matrix that at any entry in the intersection of SI and TI you get a 1, and everywhere else you get a 0. Okay. So what this so now let me rephrase what this theorem says. It says that again for any graph you can find these cut matrices, at most 1 over epsilon squared cut matrices, such that a linear combination of them approximate the adjacency matrix up to this epsilon n squared error, and this approximation is in the cut norm. So what is the cut norm of a matrix? It's basically the worst. Okay, you can think of it this way. It's the worst cut you can imagine on that matrix, or think of it as the worst triangle. Okay, so for every S and T triangle on your matrix, look at the summation of the entries in that triangle, and that would be your error. Okay, so if you want to, you can think of it in terms of graphs. Like if A is a graph and C is a matrix, the cut. If you look at this difference, the cut norm says that what is the worst cut in this graph. If you look at if the weight of each edge is the difference in the two matrices. Okay. Now, okay. So what this theorem says is that you can very well approximate every cut of your matrix with this linear combination of cut matrices, or every cut in your graph with this linear combination of cut graphs. Up to this epsilon n squared error. Now, if you have a dense graph which has n squared or order of n squared edges, that is enough to get a multiplicative approximation for max cut, to approximate the largest cut in the graph. Basically, the only thing you need to know is that how many vertices of each of these cuts is on the left side of the optimum solution. So you can solve that using like linear programming and many other tools, and that would give you a sort of so-called polynomial time approximation scheme. You can get a 1 plus epsilon multiplicative approximation for these problems. Okay, so we have 5 more minutes, or should I finish right away? 3 minutes. Okay, so let me. Okay, good. So let me finish it up. So this is the theorem we proved that for any graph G. This thing is probably not ideal because of this dependency to n squared. Okay. Now what we prove is that for any graph G, you can find these cut matrices that very well approximate your adjacency matrix, but this time as a epsilon times the number of edges. So this is a very ideal approximation because even if your graph is very sparse, you get that across every cut, this linear combination very well tells you what the size of that cut is. Okay. Now the question is how many matrices do you need? And what we need here is that is just the threshold rank of the graph over epsilon squared. Okay. And okay, once you have this, again the same things follow. You can use it to approximate maximum cut and several other problems in low threshold rank graphs. Now before I say the proof of this, you can at least I guess imagine how the proof should go. Low threshold rank graphs are union of expanders. Now in every expander, if I just give you the expanders, you can just have a cut matrix on that expander that very well approximate the expanders. So you just need the number of expanders to approximate the cuts between the expanders. Okay, so within the expanders, expander mixing lemma kind of tells us what is going on. So you just need to pay for cuts between the expanders, and because there are only this many expanders, okay, you only expect so many cuts. Okay, so many cuts over epsilon squared. Okay, that's sort of the high-level intuition behind this theorem. But the proof actually doesn't need you to give me the partitioning into expanders. It's more straightforward, and it builds on the this machinery of Friesen Cannon. So So it's a two-slide proof. So here's the first slide. So first you do a low rank approximation of your adjacency matrix. So let's say your adjacency matrix is just summation of lambda IV transpose. Then let's say B is a low rank approximation of A. That is, I drop all of the small eigenvalues and I only keep the big eigenvalues. Now, the claim is that A and B are very close in the cut norm, and a proof essentially is a Cauchy-Schwarz application. So if you look at any set S and T, the cut norm is exactly this. Okay, this is the indicator vector of the set S, indicator vector of the set T, and this is exactly like the worst over all of the set T of this quantity, all of the sets S and T of this quantity is exactly the cut norm. Now, okay, we can use Cauchy-Schwarz and say this inner product is just the norm of indicator of S times the norm of this vector. Use another, now use the, okay, good. Now use the operator norm of this matrix. So this quantity is at most the operator norm times the norm of the indicator vector of T. And then you just plug everything in. So the norm of indicator of SZ is at most root 10. Norm of indicator vector of SZT is at most root 10. This matrix is a low rank matrix. Its largest eigenvalue is at most epsilon because I dropped every small eigenvalue from A in B. So the largest eigenvalue of this matrix is at most d epsilon. So you just multiply everything in, you get epsilon times E. Okay, so basically, so the details doesn't matter. Basically, the point is that you can approximate A by a low rank matrix that only has, so B has only rank of epsilon many eigenvalues, such that every cut is in A is very well approximated by B. Okay, and now the only thing you need to show is that if you give me any matrix B, I can approximate the matrix B by linear combination of cut matrices, such that the number of cut matrices that I need is only proportional to the Frobenius norm of B. Okay. So that's the only lemma that we need. And once you have this, you know that the Frobenius norm of B is small because every eigenvalue is at most 1. And I have only rank of epsilon many eigenvalues. It's a low rank matrix. So this Frobenius norm is at most rank of epsilon. Okay. So we're running out of time. Okay, so let me just. Okay, so you just need to prove this lemma, and the proof is a simple induction. Basically, all you need to do is that, okay, say so far you have found these matrices, then you say either I'm done or there is a bad cut. Let's say S and T gives you the bad cut, such that this difference is more than the optimum error you're looking for. What you do is that you say, okay, just let this bad cut be my next cut matrix, and you choose the corresponding coefficient to be such that at least on that particular cut matrix the error is 0. So this is a normalized constant such that the error between your matrix C and the target matrix B is 0 across the cut that I just find. Now you do the calculation. You just need to use a potential function, and this is probably the most interesting part of the proof. You need to use the same Frobenius norm as your potential function. Okay. So amazingly, if you use this, nicely things cancel out, and you get that the potential function for the new matrix, that after you add the new cut matrix, is epsilon squared less than the potential matrix, the potential of the matrix that you started with. So once you have this, you'll be done in only 1 over epsilon squared this many iterations. Good. So all right. So I'm going out of time. Let me there's just a few remarks you can just see. So the proof I just said for this regularity lemma nicely generalizes to weighted non-regular graphs. Just need to use some notation and some correct generalizations. We can make it algorithmic using this nice result of Alon and Naur, who gives approximation algorithms for a cut norm. And it gives you a very fast algorithm to approximate max cut, max bisection, and these low threshold rank graphs. And let me stop here.
Thank you. Since we've run a little over, if you have questions, please ask Cheyenne at another time offline.